In the last video, we saw how we are performing Lebesgue integration starting with a bounded positive function like this. We take a partition over here and then we approximate the function with a simple function from below and a simple function from above. I have shown only the function that approximates it from below, and then we try to find the total area under these functions, something like this area. Now in this picture they just look like rectangles, but you have to understand that some of these bases need not be just simple intervals, they may be complicated sets. And since we plan to find the area of such a rectangle as height of the rectangle times length of the base, and the base need not be an interval, so we have to make sure that the base is something for which we can define length. Now in the last few videos we have seen that not all subsets of R, or in this case all subsets of the interval a to b, has the valid concept of length associated with it. So we have to choose our bases in such a way such that our bases are of that special type. We have called the set of all the subsets of a to b with a valid definition of length by the symbol script b, which we call the Borel sigma algebra. So when we are approximating, we just have to make sure that all the bases belong to this set. It is not that any arbitrary simple function will do. We need simple functions where these things, we are controlling these partitions, as a result these things are getting determined, but we have to just make sure that these things belong to script B. So let us write down mathematically how a typical such simple function would look like. Suppose I give it a name Sx, then it consists of some finitely many values. Each value is taken over a certain set that need not be an interval but must be member of script B. So I will write it in this way. I will put a summation over all the possible values. So I will write from I1 to whatever are the values. In my case it is 1, 2, 3, 4, 5. So in general it will be k. Then I will look at each of the values in turn, call them Ci. So C1 is this, C2 is this, and C5 is that upper bound M. Now each of these is taken over a certain set only. I will use the indicator function notation 1 subscript bi of x. Let us understand what this means. This means this function is equal to 1 if x belongs to bi and is 0 if x does not belong to bi. So when I do this sum, you take x. All these bi's are obviously disjoint. So in my case, C1, so when is the value C1 taken? It is taken over here. So this set is my B1. The C2 is taken over here and over here. So union of this and this constitutes B2. Similarly, C3 is where I take this value. So this is my B3. This is my B4. And what is B5? The value of M is not taken at all. So that will be just the empty set. You see all these bi's, the way I am doing it, they are actually all disjoint. So without loss of generality, I can put the extra assumption that bi's are all disjoint, and of course we have the all important condition that each bi must be in script B, what is called measurable. So each of these things must be measurable. So when we first thought about Lebesgue's approach, we just thought about any simple function, but now we are restricting ourselves. We are saying we will only work with such simple functions. Still that set is pretty rich, and all the things that you had hoped for will come to be true, but we have to put some restraint so that we can work out the total area for the blue region. Now exactly the same thing works for the upper thing, because there also we'll have the same BIs here, and depending on which things we are working with, maybe either this or this, so we'll have something again of this form. So henceforth, whenever I talk about a simple function, you understand that I have these two conditions. This is a real condition and this is just without loss of generality. I am taking the BIs to be distinct. I can take the BIs to be disjoint and the CIs to be distinct. Here is one exercise for you. I have given you a simple function C1, C2, C3 and B1, B2, B3. It is defined over the closed interval 0 to 6. So that is a simple function. However, it violates the condition that all the CIs are not distinct, 2 repeats, and all the BIs are also not disjoint. I said that you can always, without loss of generality, express a simple function with those additional constraints where these constants, DIs, are distinct and these sets, SIs, are disjoint. So your job is to express this function as this. So you have to again split it up into some indicator functions times some constants. How many you decide? K many. That need not be same as 3. Such that you get the same function, but the SIs will all be disjoint and the DIs will all be distinct.